It begins not as a sound, but as a feeling, a pressure in your ears, a vibration in your chest so profound, so deep it seems to emanate from your own bones. You might be lying in bed in the profound stillness of 3 a.m., when the world outside is muted by darkness and sleep. That's when you first notice it. A faint, persistent, low-frequency thrumming, an engine running with no engine in sight. At first you dismiss it. It must be the refrigerator or the heating system kicking in. Perhaps it's distant traffic, its rumble carried on the night air. You get up, you walk through the silent house, you press your ear against the cold metal of the appliance, you stand by the window. But the source is elusive. The noise isn't times out there, asterisk. Somehow, impossibly, it feels like it's inside the room with you. It feels like it is inside your own head. This is the hum. An auditory ghost that has haunted specific corners of our world for decades, a phenomenon as maddening as it is mysterious. It is an acoustic shadow falling upon disparate communities separated by thousands of miles of ocean and continent. From Taos, New Mexico, a high desert town steeped in art and mystery, to Bristol, England, a city of maritime history and modern industry. From Windsor, Ontario, across the river, from Detroit's industrial heartland to Bondi Beach in Australia, where the roar of the Pacific should drown out any sound so subtle. In these places and in dozens more, a small fraction of the population, typically around 2%, began to report the same unsettling experience. They hear what no one else can. For these hearers, life is irrevocably altered. Sleep becomes a battleground, a nightly siege against an invisible enemy. Concentration shatters. The quiet moments you once cherished for reading or contemplation are now filled with a monotonous, oppressive presence. Imagine a single low note on a colossal church organ held down indefinitely just at the very edge of your hearing. It is a sound that cannot be escaped. Closing the windows does nothing. Soundproofing the walls is futile. It seems to disregard the physical laws of acoustics passing through brick and glass and flesh as if they weren't there. The psychological toll is immense, a slow erosion of sanity. You try to explain it to your family, to your friends, to your doctor. They listen, they try to understand, but they hear nothing. They offer well-meaning but useless explanations. It's probably just tinnitus, they say, an internal ringing that has a clear medical origin. But this isn't a high-pitched squeal. This is a bass note from an orchestra that doesn't exist. It feels external, an intrusion from the outside world. You become the crazy one, the person obsessed with a phantom. The experience is a profound form of gaslighting, not by a person but by reality itself. The world tells you there is silence, but your own senses scream otherwise. This deep isolation, this feeling of being out of sync with everyone around you is often more painful than the hum itself. Some have been driven to desperation, abandoning their homes, selling their property at a loss, becoming nomads in a search for a silence they may never find again. They are refugees from a sound that has no scientifically accepted source. And that is the core of this enigma. We live in an age of unprecedented surveillance. We have seismometers that can detect the footsteps of a distant herd of elephants. We have hydrophones that can hear the groaning of tectonic plates miles beneath the ocean floor. We have satellite networks and sensor arrays capable of monitoring the planet's vital signs with breathtaking precision. Yet the hum persists a defiant anomaly in our data-drenched world. It is a signal without a transmitter. For decades, the search for the hum's origin has been a masterclass in frustration. Every plausible theory has been meticulously investigated, and one by one has been found wanting. The first and most obvious suspects were industrial. Large-scale manufacturing plants, power generators, compressor stations, these are all known to produce powerful low-frequency noise. Investigators armed with parabolic microphones and spectrum analyzers descended on afflicted towns. They measured the acoustic output of every factory, every pump, every fan. In a handful of cases, a specific culprit was identified and silenced, bringing relief to a small community. But these were the exceptions, the low-hanging fruit. For the vast majority of hum locations like Taos, the acoustic environment was found to be remarkably quiet. There was no industrial behemoth to blame, no single machine capable of generating a sound that could plague an entire region. The search came up empty. Next, scientists turned to geology. Could the hum be the result of microseisms, tiny imperceptible earth tremors generated by the pounding of ocean waves on continental shelves, a constant vibration in the planet's crust? This was a tantalizing idea. It would explain the low frequency and the persistent nature of the sound. Seismometers were deployed, data was correlated, and while the Earth certainly does have its own permanent low-level rumble, the specific frequency and character of the hum did not match. Furthermore, it failed to explain the most peculiar aspect of the mystery. Why can only 2% of the population hear it? A geological vibration should be felt, if not heard more uniformly. The theory, while elegant, simply didn't fit the highly localized and strangely selective nature of the phenomenon. It was another dead end in a growing labyrinth of failed hypotheses. The investigation then turned inward to the hearers themselves. Could the hum be a collective psychoacoustic phenomenon, a kind of mass hysteria or a shared auditory hallucination? This explanation is deeply unsatisfying, not least because it dismisses the very real suffering of thousands of credible witnesses. Their testimony is remarkably consistent across cultures and continents. They describe the same frequency range, typically between 30 and 80 Hz. They report the same maddening persistence, its tendency to be worse at night and indoors, away from the masking sounds of the everyday world. Crucially, when the hum has been recorded by sensitive equipment, it appears on the instruments exactly as the hearers describe. It is a real physical wave of sound pressure moving through the air. It is not imagined. The mystery is not that people are hearing things. The mystery is that the thing they are hearing has no identifiable cause. Other theories have been floated, each more exotic than the last. Could it be the combined resonance of high-pressure gas lines vibrating in concert across a national grid? Plausible, but it doesn't account for the hum's appearance in remote areas far from such infrastructure. Could it be related to extremely low frequency or ELF transmissions used by militaries to communicate with submerged submarines? Governments have repeatedly denied that any such transmissions could account for the specific characteristics and locations of the hum. Every avenue of investigation, every logical path, seems to lead to a frustrating, impenetrable wall. The hum is a perfectly self-contained paradox. It is demonstrably real but seemingly impossible. It exists just at the threshold of human perception, a cosmic whisper that our instruments and our understanding are not yet sensitive enough to fully decode. It is a message in a bottle written in a language of vibration that we have not yet learned to read. For years, the problem has remained stubbornly terrestrial. We have scoured our factories, our geology, and even our own biology for an answer that lies just out of reach. We have confined our search to the surface of our world, operating under the perfectly reasonable assumption that a sound heard on Earth must originate from Earth. But what if that assumption, the very foundation of this entire search, is wrong? What if, after exhausting all possibilities on our own planet, the only direction left to look is up? It is a breathtaking, almost heretical leap of imagination. To suggest a connection between a localized terrestrial acoustic anomaly and the vast silent emptiness of interplanetary space seems at first glance to be the very definition of a fringe idea. Science, after all, progresses through careful incremental steps, building upon established facts. But when the facts lead nowhere, when every conventional model fails, perhaps it is time for a bolder hypothesis. Perhaps we are not dealing with the noise of our civilization, but with an echo from the cosmos. To even begin to comprehend how this might be possible, we must first update our understanding of the solar system. For centuries, we pictured it as a closed, isolated system, a neat, orderly clockwork of planets orbiting a solitary star sealed off from the greater galactic neighborhood. But we now know this vision is incomplete. Our solar system is not a fortress, it is a crossroads. It is constantly moving through the Milky Way, passing through interstellar dust clouds and streams of gas, and occasionally it receives visitors. Objects forged in the crucible of another star system, wandering the galaxy for millions or even billions of years before a chance encounter brings them tumbling through our backyard. In 2017, we met the first of these confirmed travelers. It was a bizarre cigar-shaped object, dark and reddish, tumbling end over end as it raced through our solar system. It was named Oumuamua, a Hawaiian word for scout or messenger from afar. Oumuamua defied easy classification. It wasn't quite a comet. It had no visible tail of gas and dust. It wasn't quite an asteroid. It accelerated away from the sun, as if pushed by some unseen force, a phenomenon known as outgassing, though none was detected. Its trajectory was unambiguous. It came from the direction of the star Vega, and it was heading back out into the interstellar darkness, never to return. It was a profound moment, a turning point in astronomy. For the first time, we held physical proof that the stuff of other solar systems could and does pay us a visit. We were not alone, not in the sense of intelligent life, but in the sense that the materials of the galaxy are shared. Just 2 years later, a second interstellar guest arrived. This one, named 2I, Borisov, was more familiar. It was clearly a comet, albeit one with a chemical composition slightly different from those born in our own system. Borisov was a comforting confirmation. It proved Oumuamua was not a once-in-a-lifetime fluke. Interstellar objects are a regular, if infrequent, feature of our cosmic environment. Our telescopes, growing more powerful by the year, were finally able to spot these faint, fast-moving intruders. The gate to the galaxy had been opened, and it raised a tantalizing question. How many others have passed through unnoticed before our sentinels were sharp enough to see them? How many are passing through right now? And this is where our story takes its speculative turn, where the intractable mystery of a low-frequency hum on Earth intersects with the very frontier of astronomical discovery. Deep within the reams of data from our automated sky surveys programs designed to hunt for asteroids and comets that might pose a threat to Earth, astronomers have been finding hints, faint glimmers, subtle gravitational nudges on the orbits of our own outer planets. Anomalies in the data that suggest the presence of a third massive object, one that has not yet been directly imaged or confirmed. It is a ghost in the machine, a statistical probability in search of a telescope to make it real. Provisionally, this candidate has been designated 3I, ATLS, 3I for the third interstellar object, Atlas for the survey system that may have captured its fleeting shadow. Unlike Oumuamua or Borisov, which were relatively small fleeting visitors on a hyperbolic trajectory, the models for 3I, Atlas, suggest something far stranger, something much, much larger. An object perhaps hundreds of kilometers in diameter, a true leviathan from the interstellar deep, and its trajectory might not be a simple flyby. Some models suggest it could have been captured by our sun's gravity, entering into a vast, eccentric, chaotic orbit that swings it far out into the Oort cloud and then brings it plunging back into the inner solar system over immense timescales. A captured relic from another star, now a permanent, if elusive member of our own solar system. Here is the daring question that forms the heart of our investigation. What kind of signature would an object like this produce? A conventional asteroid or comet is for the most part gravitationally and electromagnetically quiet. But an object of this theorized size and potential composition, perhaps rich in metallic iron or possessing a strange magnetic field forged in the heart of an alien nebula, its interaction with our solar environment could be profound. As it nears the sun, it would plow through the solar wind, the constant stream of charged particles flowing from our star. Could this interaction create a colossal magnetohydrodynamic bow shock? A standing wave of immense energy vibrating at an incredibly low frequency. Think of it like a bell of planetary proportions. The sun's magnetic field and the solar wind are the medium. The passage of this massive anomalous object, 3I, Atlas, is the strike. And the result is a resonance, a vibration that propagates outward through the interplanetary medium, a hum, a cosmic hum, generated far beyond the confines of our atmosphere. Could this wave of infrasonic energy travel the 150 million kilometers to Earth? And could it, upon arrival, be focused and amplified by the unique properties of our own planet's magnetic field and ionosphere? Perhaps certain geographic locations due to their underlying geology, or their specific position relative to the Earth's magnetic poles, act as natural resonant cavities. Like the body of a violin, they are perfectly shaped to take this faint, imperceptible cosmic vibration and amplify it into something that can, by a sensitive few, be felt, be heard. This is a hypothesis that exists on the very edge of science. It connects the smallest scales of human sensory experience with the largest scales of celestial mechanics. It proposes that the maddening noise in a quiet bedroom in Bristol could be an echo of a silent giant, a dark messenger from a forgotten star, as it makes its lonely pilgrimage through our home system. It is a story that, if true, would change our perception of the world. It would mean that the most persistent and localized mystery on Earth has the most universal and distant of origins. The hum would be revealed not as a malfunction of our technology or a flaw in our perception, but as a genuine physical connection to the greater galaxy. A signal not of intelligence, but of presence. A constant low-frequency reminder that our solar system is larger, stranger, and far more interconnected than we have ever dared to imagine. The search for a terrestrial source may have failed for one simple reason: we were looking on the wrong world entirely. It begins as a nuisance, a faint, insistent thrum you might mistake for a distant engine or a neighbor's malfunctioning appliance. You strain to place it, to give it a name and a source, because to name something is to control it. But the engine never arrives, the refrigerator is fine, and the sound remains. It is a low-frequency drone, a persistent physical presence in the air, felt as much as it is heard. For most of us, this is a fleeting moment of auditory confusion. For a growing, tormented global minority, it is the soundtrack to their lives, a relentless, maddening hum that the rest of the world cannot hear. This is not a story about noise. It is a story about a sound that should not exist, an acoustic ghost haunting the quiet corners of our planet, a phenomenon so pervasive, yet so elusive, that it pushes the boundaries of perception and challenges our understanding of the very world we inhabit. It has been called the Taos hum, the Bristol hum, the Windsor hum, but these are just local chapters in a sprawling planetary mystery. A mystery that starts not in the cosmos, but right here under our feet, in the air we breathe, and perhaps even within ourselves. Before we could even conceive of looking for answers in the heavens, we first had to exhaust every possibility on Earth. The search began in the places where the hum was most acute, communities that became unwilling laboratories for a global enigma. One of the earliest and most documented hotspots is Taos, New Mexico. Here, in this high desert community known for its tranquil beauty and artistic soul, a dissonant note entered the symphony of silence in the early 1990 seconds. Residents began reporting a persistent, low-pitched sound. They described it with a desperate poetry: the idling of a diesel truck that was never there, the drone of a distant cement mixer, the throb of a cosmic bass note. For those who could hear it, known as hearers or hummers, life was irrevocably altered. Sleep became a battleground, quiet contemplation a form of torture. The local government, besieged by complaints, launched one of the most comprehensive investigations into the phenomenon ever attempted. Researchers from the University of New Mexico, armed with an arsenal of sensitive acoustical equipment, descended on the town. They set up microphones in homes in the vast open desert in soundproof chambers. They were hunting for a culprit, a tangible source they could measure, analyze, and ultimately silence. The results were maddeningly inconclusive. The sensitive equipment, capable of detecting the faintest whispers of sound, picked up nothing. At least nothing out of the ordinary that could account for the pervasive disturbance. There was no single identifiable acoustic signal that correlated with the residents' experiences. It was as if the hum existed in a perceptual blind spot for our technology, a phantom frequency that could torment a human ear but evade a sophisticated microphone. Some hearers were even placed in audiology booths, confirming their hearing was in fact exceptionally acute in the low frequency range. They weren't imagining it, they were perceiving something real, something the instruments were deaf to. The Taos investigation became a template for the frustration that would follow. It was a clear demonstration that the usual suspects' local industry traffic power lines were insufficient explanations. The mystery was deeper, more complex, and far more personal than anyone had anticipated. Across the Atlantic, another community was wrestling with its own version of this auditory plague. In Bristol, England, a city with a rich industrial history, reports of the Bristol hum had been circulating for decades. Here the sound was often described as a pulsing or throbbing, a deep vibration that could rattle windows and disturb sleep patterns for miles around. Again, investigators were called in. They pointed fingers at industrial fans, at local factories, at gas pipelines, at the complex interplay of urban noise, and for a time it seemed they had found a culprit. One large factory was identified as a significant source of low-frequency noise. Modifications were made, the noise was reduced, and the city breathed a collective sigh of relief. But the relief was short-lived. For many, the hum persisted unchanged, undiminished. It was as if the industrial noise had merely been a mask, a convenient scapegoat for a more fundamental and mysterious source. The Bristol and Taos cases underscore the central paradox of the hum. It is both a deeply localized phenomenon tied to specific geographic locations and a strikingly global one, with nearly identical descriptions cropping up in Largs, Scotland, Bondi, Australia, and Kokomo, Indiana. This pattern forces a critical question: are these all isolated, unrelated incidents with local causes, or are they all localized manifestations of a single global phenomenon? The search for an answer has led scientists down a rabbit hole of terrestrial possibilities, each more complex and intriguing than the last. The most intuitive and frequently investigated hypothesis is, of course, industrial noise. Our modern world is a symphony of mechanical sound. We are surrounded by a constant low-level drone generated by power plants, high-voltage lines, complex HVAC systems, and the ceaseless motion of transportation. These sources produce vast amounts of acoustic energy, much of it in the very low-frequency VLF and infrasound spectrum, below the typical range of human hearing, but not necessarily below the range of human perception. It is this infrasound that is often blamed for the physical sensations reported by hummers: the rattling in their chest, the vibrations in their homes, the feeling of pressure on their eardrums. Scientists have measured the emissions from industrial gas compressors, which can create powerful tonal hums at specific frequencies, like a single monstrous note held indefinitely. These sound waves can travel for astonishing distances, particularly at night when atmospheric conditions create a kind of sonic duct, allowing low-frequency sounds to propagate for dozens, even hundreds of miles with little attenuation. It's a compelling theory. It's tangible. You can point to a factory, a power station, or a wind farm and say, "There, that is the beast making the noise." In some specific cases, this has proven to be the correct answer. In Kokomo, Indiana, a comprehensive study successfully traced the town's hum to two distinct industrial sources: a cooling tower at a Daimler Chrysler plant and an air compressor intake at a Haynes International facility. Once these sources were identified and mitigated, the reported hum vanished for many residents. It was a rare and celebrated victory in the frustrating war against the hum, but these victories are the exception, not the rule. The industrial noise theory, for all its logic, crumbles when faced with the full scope of the phenomenon. What about the hum heard in the remote tranquility of the New Mexico desert, miles from any significant industrial activity? What about the hums that predate the machinery blamed for them? Perhaps most damningly, why can only a fraction of the population in a given area perceive it? If the industrial fan is pumping out a powerful low-frequency tone, it should be detectable by anyone with functioning ears, and certainly by sensitive acoustical equipment. Yet time and time again we see the same pattern: a handful of tormented individuals and a team of baffled scientists with silent instruments. Industrial noise is undoubtedly a real issue, a form of pollution that affects many. However, it cannot be the universal source. It is a piece of the puzzle, but not the key that unlocks the entire mystery. The failure of this straightforward explanation forced investigators to consider a far grander and more powerful machine: the planet itself. What if the hum is not the byproduct of human activity, but the sound of the Earth's own inner workings? This is the domain of geophysics, and it offers a tantalizing, almost poetic alternative. Our planet is not a static rock. It is a dynamic living system, a colossal engine of molten rock and shifting plates constantly generating and releasing energy. This energy doesn't just manifest as violent earthquakes, it also creates a constant subtle vibration, a planetary tremor known as microsisms. These are tiny continuous seismic waves that ripple through the Earth's crust, making the ground beneath your feet rise and fall by minuscule amounts thousands of times a day. While far below the threshold of direct human perception, this constant geological activity generates acoustic energy. Could it be that certain individuals in certain locations with unique geological compositions are somehow sensitive to this deep earth drone? The sound could be transmitted through the ground directly into their homes, making their houses act like giant unintentional tuning forks, amplifying the planetary vibration into an audible hum. An even more powerful source of this planetary background noise comes from the oceans. Imagine the ceaseless collision of massive ocean waves. When two opposing wave trains meet in the open sea, they can create a standing wave, a titanic oscillation of water that pushes down on the seafloor. This rhythmic, piston-like pressure generates powerful infrasonic waves that travel through the planet's crust. This hum of the Earth is a well-documented phenomenon, a real measurable signal that fluctuates with the seasons and storm patterns. It is, in essence, the planet's heartbeat, a constant thrum generated by the churning of its vast oceans. For most of us, this global chorus is utterly imperceptible, drowned out by the noise of our daily lives. But could the hum reported by hearers be a localized, amplified version of this very phenomenon? Perhaps specific coastal geographies or underwater topographies like submarine canyons or continental shelves can act as acoustic lenses, focusing this diffuse oceanic energy towards a single point on land, like a parabolic microphone aimed at a city. This theory is compelling because it accounts for the hum's mysterious elusiveness. It's a vibration that originates from a vast distributed source, making it nearly impossible to pinpoint. It would explain why the sound seems to be everywhere and nowhere at once, and why its intensity can wax and wane with no apparent local cause, perhaps influenced by distant storms half a world away. Yet, like the industrial theory, the geological explanation leaves critical questions unanswered. It still doesn't adequately explain the intensely personal and selective nature of the perception. If the very ground of Bristol is vibrating, why don't all Bristolians feel it? Why does it torment one person while their partner sleeping beside them hears nothing but perfect silence? The discrepancy between the physical reality of the vibration and the subjective reality of the perception remains the central confounding issue. This gap leads us from the solid ground of geology into the far more complex and controversial territory of human biology and psychology. When external explanations fail, it's natural to turn the investigation inward. Could the source of the hum lie not in the environment but within the hearers themselves? This is an incredibly sensitive and often misunderstood area of research, as it can easily be misinterpreted as dismissing the sufferer's experience as all in their heads. But the science here is not about imagination. It is about the intricate mechanics of human perception. The most common medical explanation proposed is a specific form of tinnitus. Tinnitus is the perception of sound when no corresponding external sound is present. Most people experience it as a high-pitched ringing, but it can manifest in countless ways, including a low-frequency hum. It can be caused by hearing damage, neurological issues, or even stress. From a purely clinical perspective, the description of the hum aligns perfectly with low-frequency tinnitus. It's internally generated, inaudible to others, and can be incredibly distressing. This explanation seems neat and tidy, but it's deeply unsatisfying to the hearers. Many of them report that the hum is directional. They can point to where it's coming from. It gets louder in certain rooms of their house and quieter in others. They insist it is an external, not an internal phenomenon. Crucially, some hearers have found that they can escape the hum by traveling away from their home area, a fact that directly contradicts the idea of a purely internal physiological source like tinnitus. A more nuanced theory involves a phenomenon known as spontaneous otoacoustic emissions, or SOAEs. The human ear is not just a passive receiver of sound, it is an active biological machine. The cochlea, the spiral-shaped organ in the inner ear, contains tiny hair cells that amplify faint sounds. In some people, these hair cells can oscillate and produce their own faint, audible sounds. These are real, measurable acoustic signals that can be picked up by a sensitive microphone placed in the ear canal. Could the hum be a case of a person's brain perceiving their own otoacoustic emissions? This theory is intriguing because it bridges the gap between the internal and external. The sound is generated by the body, but it is a real physical vibration, not a neurological phantom like tinnitus. It could potentially explain why only some people hear it. They are the ones with particularly active SOAEs. However, the sounds produced by otoacoustic emissions are typically very faint and high-pitched, which doesn't align well with the deep, powerful house-rattling drone described by most hummers. This leads to the most controversial explanation of all mass psychogenic illness, formerly known as mass hysteria. This is a phenomenon where a group of people connected by a shared anxiety begins to experience similar physical symptoms without a clear medical cause. The theory suggests that once the idea of the hum enters a community's consciousness through media reports, suggestible individuals might begin to misinterpret ambiguous background noises as the mysterious phenomenon. The brain is a powerful pattern-matching machine. Once it's been told to listen for a hum, it may start to find one everywhere. This theory is almost always rejected outright by the communities of hearers who feel it dismisses their very real suffering as a form of collective delusion. They are not anxious or suggestible people. They are ordinary individuals whose lives have been hijacked by an unwanted sound. While psychological factors undeniably play a role in how people cope with the hum, the stress and anxiety it causes are immense. Labeling the entire phenomenon as a psychogenic illness feels like an intellectual surrender. It is an admission of defeat, a way of closing the case on a mystery we simply lack the tools to solve. And that is where conventional science has left us. We are faced with a global mystery and a collection of incomplete, mutually exclusive explanations. Industrial noise is a real factor, but only in some cases. Geological vibrations are a certainty, but the link to human perception is tenuous. Physiological and psychological factors are undeniably at play, but they fail to account for the consistent, geographically specific nature of the reports. Each theory explored in isolation falls short. Each investigation ends not with a conclusion, but with a frustrating question mark. It seems the hum is a multi-headed beast, a phenomenon that cannot be slain with a single sword. This exhaustive, frustrating search for a terrestrial cause, this process of eliminating every logical culprit here on the ground, has served an unexpected purpose. It has forced us to accept the profound limitations of our perspective. It has systematically proven that the answer may not lie in our factories beneath our feet, or even within our own minds. By ruling out the Earth, we have by necessity been forced to lift our gaze. If the sound is not coming from below, then we must consider the one direction we have so far ignored. We must look up. To solve a mystery rooted in sound, in a vibration felt more than heard, we cannot rely on our own flawed senses alone. The anecdotal evidence, the personal torment of the hum, takes us only to the edge of the known world. To go further, to truly interrogate this global phenomenon, we must learn to listen with an entirely new kind of ear. We have to tune ourselves to a frequency that exists beneath our own reality, a ghostly channel broadcasting the secret life of our planet. This is the world of infrasound, frequencies so low, so profound, they fall off the cliff of human perception. Below 20 Hz, sound ceases to be an event you simply hear with your ears. It becomes a pressure wave, a pervasive vibration that can travel immense distances, passing through buildings, bending around mountains and rolling across entire continents with almost no loss of energy. This is the planet's native tongue, the bass note of geology, meteorology and physics. It is the language of forces so vast they dwarf our own existence. A volcanic eruption in Indonesia does not just send ash into the sky, it broadcasts a thunderous subaudible warning that circles the globe for days. The immense energy of two dueling ocean storms in the mid-Pacific generates a constant, powerful drone, a pressure wave that pulses against the shores of every landmass on Earth. For most of human history, this symphony of the unheard played on completely unnoticed. We were deaf to the planet's deepest conversations. But that all changed in the chilling silence of the Cold War. In an era of secrets and suspicion, the superpowers sought a way to police the world, to detect the one thing they feared most, a clandestine nuclear detonation. An atomic bomb unleashed in the atmosphere creates more than just a flash and a mushroom cloud. It is a profoundly violent acoustic event. It rips a hole in the air, sending out a shockwave of immense power, a shockwave that announces itself across the infrasound spectrum. This terrifying realization gave birth to a new science of listening, Born from paranoia, a global network of exquisitely sensitive instruments began to spread, a web of mechanical ears planted in the quietest, most remote corners of the world, their secret mission to listen for the whisper of Armageddon. The technology they employed was not merely a microphone. You are likely picturing something that captures sound as you know it, but these devices, these microbarometers, are infinitely more delicate. Imagine a sensor so finely tuned it can detect a change in air pressure equivalent to the weight of a single feather resting on the palm of your hand. Now imagine that sensitivity amplified 1,000 times over. These are instruments designed to feel the very breath of the atmosphere. But a single sensor is little more than a lonely outpost, a blind listener. It can tell you that a pressure wave has arrived, but not from where or from what. The true genius of this global network lies in its architecture. At each monitoring station scattered across deserts, frozen tundras, and lonely volcanic islands, the sensors are not placed randomly. They are arranged in precise geometric arrays, vast patterns stretching over kilometers. These arrays function as a single cohesive listening device, a kind of acoustic antenna. When a low-frequency wave rolls across the array, it strikes each sensor at a slightly different time, a difference of mere milliseconds. It is an infinitesimal delay, yet it holds the key. By comparing these microscopic time lags across the entire array, supercomputers can perform a kind of celestial trigonometry. They can calculate with astonishing precision the direction from which the wave arrived. They can triangulate its origin, and when you link dozens of these arrays across the globe, from Antarctica to Alaska, from Brazil to Germany, a complete picture emerges. An infrasound event, no matter where it occurs, is captured from multiple angles. Its location can be pinpointed to a specific place on the map. This is the International Monitoring System, a legacy of the Cold War now repurposed under the Comprehensive Nuclear Test Ban Treaty Organization, or CTBTO. It stands today as one of humanity's greatest scientific achievements, a planetary-scale sensory organ perpetually listening. Initially, its purpose was singular, to ensure no nuclear test went undetected, and it has succeeded beyond all expectation. When North Korea has conducted its underground tests, the shudder of the Earth is one signal. But the almost imperceptible ripple it sends through the atmosphere, traveling at the speed of sound, is another. The network hears it. The world knows. But in the long decades of its silent vigil, this global ear began to pick up other voices. It started to catalogue the planet's natural rhythm, its groans, its sighs, its sudden shouts. Scientists tasked with filtering out the noise to find the bomb signatures realized that the noise itself was a treasure trove of information. They were inadvertently building the first ever global atlas of Earth's unheard sounds. They discovered that our world is never ever silent. Listen with these instruments for just a single day and you will witness a planet teeming with acoustic life. You will hear the low growl of an avalanche in the Alps, a sound that never reaches a human ear but travels for hundreds of miles as a pressure wave. You can detect the voice of a restless volcano like Stromboli or Etna, not as a single eruption, but as a near-constant series of deep guttural pulses, the rhythmic breathing of a sleeping giant. Each volcano, scientists have learned, possesses its own unique acoustic fingerprint, a baseline of activity that allows volcanologists to identify even the slightest change, the subtlest shift in tone that might herald a coming catastrophe. It is a planetary early warning system, written in a language we are only just beginning to decipher. The network also hears the sky fall. Every single day, hundreds of tons of rock and dust from space plunge into our atmosphere. Most are no bigger than a grain of sand burning up in a silent flash. But the larger ones, the ones we call bolides or fireballs, they announce their arrival with an infrasonic scream. In February of 2013, residents of Chelyabinsk, Russia, witnessed a light brighter than the sun streak across the morning sky. Minutes later, a shockwave hit, a deafening explosion that shattered windows, collapsed roofs, and injured over 1,000 people. It was the violent entry of a 20-meter asteroid, an event no one saw coming, but the planet's infrasound network heard it loud and clear. 20 different stations, some as far away as Antarctica, over 15,000 kilometers distant, recorded the unique low-frequency signature of the meteor's atmospheric detonation. The signals arriving hours after the event allowed scientists to reconstruct its journey, to calculate its energy equivalent to 30 times the bomb that leveled Hiroshima, and to map the path of its atmospheric disintegration with pinpoint accuracy. It was a stark reminder that we live in a cosmic shooting gallery, and that infrasound provides our only shield of awareness, a tripwire stretched across the upper atmosphere listening for intruders. Yet even these dramatic events, the volcanoes, the meteors, the distant explosions, are merely the crescendos in a much larger, more persistent symphony. The dominant sound on this planetary broadcast, the one that never stops, comes from the heart of our world's engine, the oceans. Out in the vast, empty expanses of the Pacific and the Atlantic weather systems generate colossal ocean waves, swells that can travel for thousands of miles. When two of these opposing wave trains collide, they create what is known as a standing wave. This interaction acts like a gigantic slow-moving piston on the atmosphere, pushing and pulling on the air above it with immense rhythmic force. This constant planetary-scale oscillation generates a powerful, ubiquitous infrasound signal, a deep, resonating hum centered around 0.2 Hz. Scientists call this phenomenon the microbarometer, and it is the loudest, most persistent natural infrasound source on the planet. It is the Earth's own hum, a vibration born from the ceaseless motion of water. It is the background noise of our world, the ambient track against which all other signals are measured. This discovery was profound. It revealed that our planet has a heartbeat, a rhythmic pulse generated not by geology, but by the interplay of ocean and air. This microbarometer signal is so powerful and so predictable that meteorologists now use it to track and understand the intensity of marine storms, listening to the sound of the waves from thousands of miles inland. It is a constant presence on every infrasound sensor on the globe, a signal that must be understood, accounted for, and filtered out if you ever hope to hear anything else. And this brings us to the core challenge, the central drama in the life of an infrasound scientist. Their work is a relentless quest for a signal buried in an ocean of noise. Imagine you are standing in the center of a colossal stadium during a championship game. Tens of thousands of people are shouting, roaring, and cheering. The noise is overwhelming a physical force. Your task is to isolate the sound of a single specific conversation happening in the top row on the opposite side of the field. That is the monumental task facing these acoustic detectives every single day. They are sifting through the constant roar of the ocean's microbarometers, the percussive blasts of meteors, the rumbling of distant storms, the tremors from earthquakes, the growl of volcanoes, and even the noise of our own civilization, the thrum of supersonic jets, the blast from mining operations, the rhythmic pulse of wind turbines. All of this data, terabytes of it, pours in from the global network every hour. It is a chaotic, layered cacophony. To find meaning within it requires a masterful blend of physics, computer science, and intuition. Sophisticated algorithms act as the first filter, scanning the data streams for patterns that match the known acoustic fingerprints of natural and man-made events. They hunt for the unique signature of a bolide's entry, the characteristic waveform of a volcanic belch, or the sharp, unmistakable spike of an artificial explosion. These known signals are tagged, identified, and archived. But the truly fascinating work begins with what is left over. The anomalies, the signals that don't fit, the sounds that have no immediate identifiable source. These are the moments that quicken a researcher's pulse. An unknown signal might appear on an array in South America, then minutes later be detected by an array in Africa, and then again in Australia, tracing a clear path across the globe. Is it a previously unknown atmospheric phenomenon? A new kind of meteorological event, like the recently discovered infrasound from sprites, the vast electrical discharges that dance above thunderstorms, or could it be the distant echo of a rocket launch that went unreported? The investigation is a meticulous process of elimination. Scientists cross-reference their acoustic data with satellite imagery, seismic readings, lightning detection networks, and flight path records. They become global detectives hunting for a culprit that left behind nothing but a vibration in the air. They must peel back every layer of the planet's natural noise, a process of such complexity and precision that it pushes the boundaries of our technology. We have built this extraordinary machine, this planetary ear, to listen for the threats we could create and the warnings our own planet might offer. We have taught ourselves to distinguish the voice of the volcano from the song of the sea, the cry of a falling star from the tremor of the deep earth. We have become fluent in the low-frequency language of our own world. This system is our ultimate ground truth, a network that can confirm or deny the existence of a physical acoustic event anywhere on the planet with unwavering certainty. So what happens when this network designed to listen to the Earth picks up a signal that seems to have no terrestrial origin at all? What do we do when we have eliminated every earthly suspect, every storm, every volcano, every meteor, every human-made machine, and a strange, persistent signal remains? This is precisely the precipice on which we now stand. We have the story of the hum, a deeply personal, subjective experience. And we have the rigorous, objective capability of a global infrasound network that hears what we cannot. The critical question is whether these two worlds, the human and the mechanical, are perceiving the same thing. Is the hum merely a phantom of human biology, a trick of the mind? Or is it the faintest edge of a real physical wave, a vibration so subtle that only a fraction of our population is sensitive enough to perceive it, while our instruments, scattered across the globe, record its full, unambiguous power? To answer that we must turn this incredible listening network away from the Earth. We must calibrate it not for the sounds of our world, but for a whisper from a far more profound and unnerving direction. We have to point our new ears upward toward the silent, empty spaces between the worlds and listen for the sound of a visitor passing in the night. And so, with every terrestrial avenue explored and exhausted, our investigation into the global hum had reached a dead end. The sound persisted, a planetary fever with no discernible cause, leaving us with a profound and unsettling silence, not in our ears but in our understanding. For generations we had looked to our own world for answers, assuming that any great mystery must have its roots here beneath our feet, in our oceans or in our skies. But what if the source wasn't terrestrial at all? What if to solve a puzzle on Earth, we had to lift our gaze much, much higher past the moon, past the planets, into the chilling interstellar dark? For most of human history, our solar system felt like an island, a warm, well-lit sanctuary, adrift in an incomprehensibly vast and empty ocean of cosmic nothingness. We knew, theoretically, that other stars had planets. We knew that comets and asteroids, our system's leftover rubble, orbited our sun in a chaotic but ultimately familiar dance. Everything we had ever touched, ever studied, was a native of this place. It was all family born from the same spinning cloud of gas and dust billions of years ago. The idea of a visitor, a true alien from another star system, was the stuff of science fiction, a statistical probability so remote that it barely registered in the practical world of astronomy. We had never seen one. We had no proof that such a journey was even possible. The distances are too great, the void too desolate. Our home, we believed, was fundamentally sealed off, a closed and isolated system. Then, on October 19th, 2017, that comforting illusion was shattered forever. The Pan-STARRS telescope in Hawaii, a sleepless eye scanning the heavens for rocks that might threaten Earth, flagged something impossible. It was a faint point of light moving so fast and on such a bizarre trajectory that it defied all explanation. This was no asteroid from our belt. This was no comet from the distant Oort cloud. Its path was a hyperbola, an open-ended arc that was not bound by our sun's gravity. It was screaming through our solar system at nearly 60,000 miles per hour, a speed it could only have achieved by falling toward our sun from the unimaginable depths of interstellar space. It had come from another star. We had just a few weeks to study it before it vanished back into the black, a fleeting, ghostly apparition. Astronomers around the world dropped everything, turning every available telescope toward this fleeting guest. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And the more we learned about this messenger, the stranger its message became. It was small, no more than a few hundred meters long, but its shape was unlike anything we had ever seen. As it tumbled through space, the light it reflected changed dramatically. This told us it wasn't a sphere or a potato-like asteroid. The data suggested it was bizarrely elongated, perhaps 10 times longer than it was wide, a cosmic needle, a shard of some distant, shattered world, or as some artists imagined, something more crafted, more deliberate. It was dark reddish in colour, likely the result of eons of bombardment by high-energy cosmic rays on its lonely journey between the stars. And it was silent. Scans for any kind of technological signal, any radio transmission, found nothing but the cold hiss of the void. It appeared to be a dead, inert piece of rock. But then, as Oumuamua whipped around the sun and began its journey back out, it did something that broke the known laws of physics. It accelerated. Just a tiny, gentle push, but it was undeniable. The object was speeding up, moving away from the sun faster than gravity alone could explain. For comets, this behavior is common. As they near the sun, ice on their surface vaporizes, creating jets of gas that act like tiny rocket thrusters, a process called outgassing. But astronomers looked for the signs of this outgassing around Oumuamua, for the characteristic fuzzy halo, the coma of a comet, and they found nothing. Absolutely nothing. The James Webb and Hubble Space Telescopes stared at it sensitive enough to detect a whisper of dust and gas. The void around the object remained pristine. So, what was pushing it? The scientific community was thrown into a state of bewildered excitement. Theories flew like sparks from a fire. Perhaps it was made of some exotic solid hydrogen that vaporized invisibly. Maybe it was an impossibly fluffy object, a cosmic dust bunny being pushed by the gentle pressure of sunlight itself. One leading Harvard astronomer, Avi Loeb, put forth an even more radical idea that the strange acceleration, the bizarre shape, the lack of any visible outgassing, all pointed to the possibility that Oumuamua was not natural at all. He suggested it could be a piece of alien technology, perhaps a solar sail, a light probe from another civilization, tasting the stellar winds of our system before continuing its journey. The suggestion was met with intense skepticism, as it should be. Extraordinary claims require extraordinary evidence. But the fact that such a hypothesis was even considered by a serious scientist speaks to how utterly baffling Oumuamua was. It didn't fit into any of our neat little boxes. It was a scientific enigma wrapped in a cosmic mystery, and then, just as quickly as it appeared, it was gone, fading into the darkness, leaving us with more questions than answers. Was it a fluke? A once-in-a-civilization event? A singular oddity that we were lucky to have witnessed? For 2 years it seemed that way. The silence of the interstellar void returned, but in August of 2019 it happened again. This time it was an amateur astronomer in Crimea, Gennady Borisov, who spotted the second interstellar interloper. Designated 2I, Borisov, this visitor was profoundly different from the first. As it approached the sun, it grew a magnificent coma and a long, sweeping tail. It was for all intents and purposes a comet, a perfectly normal, predictable comet behaving exactly as our comets do. Except for one crucial fact, its trajectory proved beyond any doubt that it had also come from another star system. Borisov was the confirmation we desperately needed. Oumuamua wasn't a fluke. Our solar system was not an island. It was a port of call. The galaxy, it turned out, was a vast interconnected ecosystem, with bits and pieces of distant star systems constantly silently drifting through our own backyard. These two discoveries fundamentally rewired our understanding of our place in the cosmos. We realized that we are not isolated. We are bathed in a steady, invisible rain of alien material. The implications were staggering. These objects could be seeds carrying the chemical building blocks of life from one star system to another, a theory known as panspermia. They are time capsules carrying pristine information about the chemical makeup of the planetary nurseries, where they were born hundreds of millions or even billions of years ago. To read them is to read the history of the galaxy. Suddenly, a new urgency gripped the world of astronomy. We had to find more of them. We could no longer afford to be surprised. We had to be ready. This is where the Asteroid Terrestrial Impact Last Alert System, or ATLAS, enters our story. A network of telescopes funded by NASA designed with a single solemn purpose to be our planetary sentinel. Its primary mission is to scan the entire visible sky every few nights, a relentless robotic guardian searching for any asteroid on a collision course with Earth. It is our last line of defense, designed to give us a few weeks' warning of an impending impact. But in the hunt for doomsday rocks, Atlas accidentally became something more. It became our net for catching these interstellar butterflies. Because its eyes are so wide, sweeping across vast swaths of the heavens, it is uniquely positioned to spot the faint, fast-moving objects that betray an origin beyond our sun's grasp. And it is this very system, Atlas, that is now at the heart of our investigation. Because after Borisov, the hunt intensified. Dozens of potential interstellar candidates have been flagged, their trajectories painstakingly analysed. And one of them provisionally named 3I. Atlas, the third confirmed interstellar object, is the subject of our story. The one whose trajectory, when traced back, coincided with the first pulses of the global hum. A coincidence so profound it seemed impossible. But how? How could a silent rock hurtling through the vacuum of space create a sound that could be felt in the very crust of our planet? The vacuum, after all, does not carry sound. This is where science often takes a leap of faith. Not into the supernatural, but into the unknown, guided by the breadcrumbs of data and the power of sanctified imagination. The answer, according to a small but brilliant group of astrophysicists, may not lie in the rock itself, but in its violent interaction with the environment it is passing through. You see, the space between the planets is not empty. It is filled with a tenuous, invisible, and incredibly energetic substance called the solar wind. It is not a wind in any terrestrial sense. It is a super-hot, supersonic gale of charged particles, protons and electrons constantly boiling off the surface of the sun and streaming outwards through the solar system at 1,000,000 miles per hour. It is the sun's breath, a cosmic river that shapes planetary magnetic fields, sculpts the tails of comets, and carves the very structure of our solar system. Now imagine our interstellar visitor 3I, Atlas. It is not a native of this river. Its chemical composition is alien. Its magnetic properties are unknown. Its surface has been weathered by a journey we can barely comprehend. As this foreign object plows through the solar wind at tremendous speed, it doesn't just pass through it. It disrupts it. It creates a shockwave, a cosmic sonic boom, much like a supersonic jet creates in our atmosphere. This is the domain of Dr. Harris Thorne, a planetary scientist specializing in a field that sounds like science fiction magnetohydrodynamics, the study of how magnetic fields and electrically charged fluids like the solar wind interact with one another. For years, Thorne has modeled what happens when our own asteroids interact with this solar plasma. But the arrival of interstellar objects presented an entirely new set of variables. Thorne's hypothesis, initially dismissed as fringe speculation, is as elegant as it is radical. He proposes that under very specific conditions, this interaction could generate waves. Not light waves, not gravitational waves, but something far more subtle. He believes it could create ultra-low frequency acoustic waves that propagate through the plasma of the solar wind itself. Imagine the solar wind as the surface of a vast invisible drum stretched taut across the solar system by the sun's magnetic field. Most objects, our native asteroids and comets, are like tiny grains of sand sprinkled on this drum. They create barely a ripple. But what if an object like 3I, Atlas, is different? What if it possesses a powerful intrinsic magnetic field of its own, far stronger than any asteroid we have ever measured? As this alien magnetic field tears through the sun's magnetic field embedded within the solar wind, it's like a powerful magnet being dragged across a network of sensitive wires. It doesn't just push the plasma aside, it causes it to resonate, to vibrate, to hum. Thorne's models show that this magnetic plucking of the solar wind could create a bow shock that oscillates, that pulses with a steady rhythmic beat in the ultra-low frequency range. Frequencies far, far below the threshold of human hearing, measured in millihertz, cycles per hour, not per second. These are not sound waves in a traditional sense traveling through air. They are compression waves traveling through the plasma of space, a sound carried on the solar wind itself. A deep, resonant note set off by a cosmic traveler. Thorne and his team calculated the potential frequencies. They were astonished. The resonant frequencies predicted by their models for an object with the estimated size and speed of 3I, Atlas, possessing a hypothetical but plausible magnetic field, fell squarely within the very range of the inexplicable global hum. It was a breathtaking, terrifying correlation. a potential bridge between the silent void of space and a tangible vibration felt here on Earth. The theory suggests that these acoustic waves carried on the solar wind would wash over the entire inner solar system. When this vibrating plasma wave encounters Earth, it slams into our planet's own protective magnetic shield, the magnetosphere. Our magnetosphere acts like a cosmic microphone diaphragm. The vibrations in the solar wind cause it to shudder and resonate in sympathy, transferring that ultra-low frequency energy down through the magnetic field lines that connect to our planet's poles. This energy could then couple with the Earth itself, inducing tiny sympathetic vibrations in the ionosphere, the atmosphere, and even potentially in the planet's crust. A cosmic hum born in the friction between an alien rock and the sun's breath, traveling 93 million miles across the void, to be picked up by our most sensitive instruments and felt by a handful of people as a persistent, maddening drone. But there is another, even more unsettling layer to Thorne's hypothesis, one that moves away from a simple interaction and into the realm of the object's internal nature. What if the source of the vibration is not the solar wind alone? What if the object itself is the engine? We know that comets can fracture under thermal stress as they approach the sunday. We know that asteroids can spin themselves apart. These are chaotic, unpredictable processes, but 3i Atlas appears to be generating a signal that is stable, coherent, almost maddeningly regular. Thorne has dared to ask another question. What if this object isn't just a passive piece of rock being played by the solar wind? What if it is in some way active? Could immense internal pressures built up over its interstellar journey be releasing energy in a steady, rhythmic pulse? Could there be some unknown geological or chemical process in its core? Some form of slow cyclical decay or crystallization that is causing the entire object to vibrate like a massive cosmic tuning fork. This would mean the object is a generator, a broadcaster of its own signal, which is then simply amplified and carried by the solar wind. This would explain the stability of the hum, its unwavering presence. It would transform 3i Atlas from a fascinating piece of cosmic debris into something far more profound. A celestial metronome beating out a rhythm that was born in the darkness between the stars. We are now faced with a paradigm shift in our thinking. A single, tantalizing and deeply unproven hypothesis that connects the largest scale of our cosmic environment with the most subtle and personal of human experiences. It suggests we are not just observers of the universe but participants in it, our very planet being subtly vibrated by the passage of a wanderer from an unknown sun. The theory is beautiful, it is terrifying, and it presents us with a new, urgent imperative. We have a trajectory for 3i, Atlas. We have a theory for how it might be generating the hum, but a theory is not proof. To find that, we must now turn our full attention to the object itself. What is it made of? What is its true nature? And if this cosmic hum is indeed its signature, are we listening to a geological process from a dead piece of rock, or are we eavesdropping on the mechanics of something far, far stranger? So we find ourselves teetering on the edge of a truly breathtaking idea, a concept so profound it threatens to rewrite our understanding of our place in the cosmos. We've traced the ethereal threads connecting a mysterious global hum to the arrival of an interstellar wanderer 3.1 ATLS. We've allowed ourselves to imagine the unimaginable, a form of communication, a cosmic greeting, or perhaps the unintentional byproduct of an alien technology echoing across the solar system and finding purchase in our world. It is a story that captures the deepest, most primal human desires for connection and discovery. But here, right at this precipice, science demands we pause. It asks us to tether ourselves to the hard bedrock of known physics before we leap into the beautiful abyss of speculation. For every grand hypothesis, there must be a trial by fire, a rigorous and unyielding cross-examination. We must now enter the cold, quiet courtroom of science, where extraordinary claims require nothing less than irrefutable, extraordinary evidence. The prosecution's case is formidable, built not on malice but on the fundamental laws that govern the universe itself. The first witness it calls is the most unforgiving of all the tyranny of empty space. The chasm separating our world from the path of 3i Atlas is a silence so absolute it defies terrestrial comparison. It is a void measured in hundreds of millions of kilometers, an expanse so vast that light itself, the undisputed speed champion of the cosmos, takes many minutes to cross it. Into this profound emptiness, we have projected a signal, a hum. But what is sound? At its most fundamental level, it is vibration, a pressure wave that requires a medium through which to travel. Here on Earth, we are constantly bathed in this medium. Air, water, even the solid ground beneath our feet all act as conduits carrying vibrations from a source to a receiver. You hear these words because my voice is creating pressure waves in the air which travel to a microphone, are converted and then recreated as new pressure waves by your speakers, ultimately vibrating the delicate mechanisms of your inner ear. The entire process is a physical chain of custody, a relay race of molecules bumping into one another. But in the vacuum of space, that chain is broken. The relay runners are absent. There are, for all practical purposes, no molecules to bump into. Imagine shouting at a mountain across a valley. Your voice travels, reflects, and returns as an echo. Now imagine that valley is drained of all its air, every last atom removed. You could scream until your lungs gave out and the mountain would never know. Your vocal cords would vibrate, but with no medium to carry that vibration away, the sound would die the instant it was born. This is the challenge any sound-based signal from 3i, Atlas, would face. It's not just difficult. According to our current understanding of physics, it is impossible. A conventional acoustic wave, a hum in the traditional sense, simply could not have propagated from the comet to the Earth. It would be like trying to send a ripple across a pond that has no water. The concept dissolves into absurdity, so perhaps we are being too literal. Could the hum be something else, a different form of energy that we are merely perceiving or transducing as sound? The most likely candidate would be electromagnetic waves or radio waves, which require no medium and travel perfectly through a vacuum. This is the basis for all our deep space communication and radio astronomy. But this solution immediately presents its own cascade of intractable problems. If 3i, Atlas, were broadcasting a powerful low-frequency radio wave, why have none of our sophisticated radio telescopes instruments, designed with exquisite sensitivity for this very purpose, detected it? The global network of radio, observatories from the Atacama Large Millimeter Array in Chile to the late Great Arecibo dish, constantly scans the heavens. They are our planetary ears listening for the faintest cosmic whispers. Yet from the direction of 3i, Atlas, there has been only silence. No coherent artificial signal has been logged. Furthermore, for a radio wave to generate a physical audible hum on the ground, it would need to interact with our environment in a truly bizarre and energetic way. It would have to be powerful enough to physically vibrate structures, or perhaps even the very air on a global scale. The energy required for such a feat would be astronomical, far beyond what could be produced by any natural process we've ever observed from a comet. It would have to be a celestial blowtorch of electromagnetic energy, and a signal that powerful would not be subtle. It would disrupt global communications, interfere with satellites, and be blindingly obvious to any and all of our monitoring systems. We have seen nothing of the sort. The hum, whatever it is furtive and elusive, the polar opposite of what such a powerful broadcast would be. So we are forced to consider even more exotic possibilities. Could the energy be transmitted via gravitational waves? These ripples in the fabric of space-time itself, first predicted by Einstein and only recently detected, certainly travel through the vacuum. But they are generated by the most cataclysmic events in the universe, like the collision of two black holes or the merger of neutron stars. Our multi-billion-dollar LIGO and Virgo observatories are monumental feats of engineering designed to detect displacements 1,000th the width of a proton. An object the size of 3i, Atlas, even if it were made of some impossibly dense vibrating material, would be a gravitational mute. It could not possibly generate space-time ripples potent enough to be felt, let alone heard on Earth. Every path we explore, every known physical mechanism we test, leads to a dead end. The sheer silent emptiness of space stands as a seemingly insurmountable barrier, a great wall between the interstellar visitor and the strange terrestrial phenomenon. The prosecution rests its first case, confident that the fundamental nature of the cosmos exonerates the defendant. But the trial is far from over, because even if we were to grant the impossible to imagine that some unknown form of energy, to a whisper from a ghost physics, did manage to traverse the void and arrive at the doorstep of our planet, it would then face its second great trial, the atmospheric gauntlet. Earth's atmosphere is not a gentle, welcoming envelope. It is a fortress. It is a multi-layered shield, 100-kilometer thick bastion of gas plasma and shifting magnetic fields that has protected life on this planet for billions of years. It burns up meteors, deflects solar winds, and absorbs deadly cosmic radiation. For any signal arriving from space, it is a formidable obstacle course, a filter that is exceptionally good at disrupting, distorting, and dissipating incoming energy. Let's assume some mysterious low-frequency energy wave has reached the outer edge of our world. Its first encounter would be with the ionosphere, a vast region of charged particles held captive by Earth's magnetic field. This shimmering electrical shell is notoriously fickle. It is a turbulent sea of plasma churned by the constant onslaught of the solar wind. For low-frequency signals, the ionosphere acts less like a window and more like a warped, bubbling mirror. It reflects, refracts, and scatters them in unpredictable ways. This is why long-range AM radio broadcasts can sometimes travel further at night. The structure of the ionosphere changes, allowing the signals to bounce off it and curve around the Earth. For a coherent global signal to penetrate this electrical tempest without being scrambled into unrecognizable noise would be a miracle of celestial engineering. But should our hypothetical signal navigate the ionosphere, its journey has only just begun. It must then plunge into the denser layers of the atmosphere, the mesosphere, the stratosphere, and finally the troposphere in which we live and breathe. Each layer presents its own unique challenge with different densities, temperatures, and wind shears. These are not static, placid pools of air, they are dynamic, chaotic systems. Think of trying to hear a specific quiet conversation from across a crowded, windy stadium during a rock concert. The sheer amount of background noise and interference is overwhelming. Our atmosphere is a perpetual concert of noise. Winds howl in the jet stream, creating immense continent-sized waves of pressure. Storms rage, generating their own powerful infrasound signatures from lightning and turbulence. The signal would be battered by these competing forces, its energy attenuated with every kilometer of its descent. Attenuation is the process by which a signal loses intensity as it travels through a medium. The dense air of our lower atmosphere is an exceptionally effective attenuator, absorbing and scattering acoustic and electromagnetic energy. A faint whisper arriving from space would be swallowed by the atmospheric roar long before it ever reached the ground. It would be like trying to illuminate the ocean floor with a single candle from the surface. The light is simply absorbed by the medium it is trying to pass through. The science of atmospheric acoustics makes this starkly clear. We have studied how sound travels through the air for centuries. We know, for instance, how volcanic eruptions on one side of the planet can sometimes be detected on the other. But these are among the most energetic events on Earth, releasing the power of thousands of nuclear weapons. Their infrasound waves are so powerful they can circle the globe multiple times, but they do so by traveling through specific, efficient ducts in the stratosphere, bouncing between layers of air. They do not simply penetrate the atmosphere from the top down. For an external signal from a source as comparatively minuscule as 3I, Atlas, to survive this descent and be heard globally with a consistent characteristic would require it to violate the known principles of atmospheric physics. It would need to be aimed with impossible precision, possess an energy signature that is somehow immune to attenuation and scattering, and be powerful enough to overwhelm the planet's own natural and man-made cacophony. No known form of energy has these properties. Faced with the unyielding realities of the vacuum and the brutal filter of our atmosphere, the link between the hum and 3I, Atlas, begins to look less like a plausible hypothesis and more like a beautiful but impossible piece of fiction. And it is here that the prosecution brings forth its final and perhaps most compelling line of argument: the multitude of other suspects, the terrestrial explanations that require no new physics, no alien intervention, and no cosmic coincidence. Long before 3I, Atlas ever graced our skies, people were reporting strange, persistent, low-frequency humming noises. From Taos, New Mexico to Bristol, England, the phenomenon of the hum is a well-documented, if poorly understood, feature of our modern world. And for each case, scientists have proposed a litany of prosaic, earthbound explanations. The most prominent suspect is the ceaseless thrum of our own industrial civilization. We live on a planet that is vibrating. It is humming with the energy of our own creation. Think of the vast networks of high-pressure gas pipelines that crisscross continents. The immense compressors that push the gas through these steel arteries can generate powerful, low-frequency tones. These vibrations don't just travel through the air. They are transmitted directly into the ground, using the Earth's crust as a colossal subwoofer. They can travel for hundreds, even thousands of kilometers, their precise frequency determined by the operating speed of the pumps and the resonance of the surrounding geology. It is entirely plausible that in certain locations, geological formations could act as focusing lenses, amplifying these faint industrial tremors into a perceptible hum for a small, localized population. Then there are the colossal forests of wind turbines that have risen across the globe. Each massive blade slicing through the air creates aerodynamic turbulence and a distinct infrasound signature. While a single turbine might be insignificant, a farm of hundreds, all spinning in relative synchrony, can produce a complex and far-reaching field of low-frequency noise. Researchers have documented the physical effects on residents living nearby, a phenomenon sometimes called wind turbine syndrome, with symptoms including headaches, sleep disturbance, and a perceived auditory hum. Like the pipelines, these vibrations can also couple with the ground propagating far beyond the range of audible sound. Is it not more likely that what people are experiencing is the growing sub-audible footprint of our own quest for energy, rather than a signal from the depths of space? But our technology is not the only source of planetary noise. The Earth itself has a voice. It speaks in a language of deep, resonant frequencies. Ocean waves, for instance, are a relentless source of global infrasound. As trillions of tons of water crash upon coastlines around the world, and as waves interact with each other in the open ocean, they generate a constant, powerful vibration known as microseisms. These microseisms are, in effect, the planet's heartbeat. They are a permanent low-frequency hum that seismologists must constantly filter out of their data to study earthquakes. This oceanic energy permeates the entire planet's crust. It is everywhere all the time. Could it be that under specific atmospheric and geological conditions, these ever-present microseisms can become, for a few sensitive individuals, perceptible? Perhaps a change in local topography, or even the structure of a person's own house could create a resonant cavity, an echo chamber, that amplifies a narrow band of this planetary background noise into the maddening drone of the hum. We must also confront the most intimate and complex suspect of all, our own biology. The human auditory system is an instrument of breathtaking sensitivity, but it is not flawless. Conditions like tinnitus can create the perception of sound where none exists. While typically experienced as a high-pitched ringing, some forms of tinnitus manifest as a low-frequency rumbling or humming. Spontaneous otoacoustic emissions are another fascinating phenomenon, where the cochlea of the inner ear actually produces its own faint sounds. Could the hum be, for at least some sufferers, an entirely internal experience, a phantom sound generated by the intricate and sometimes mysterious workings of our own bodies? When you assemble all these potential culprits: industrial machinery, wind farms, oceanic microseisms, high voltage power, lines, and even our own physiology, the need for an extraterrestrial explanation begins to fade. Science operates on a principle known as Occam's razor. The simplest explanation that fits all the facts is usually the correct one. An explanation that relies on the known observable and measurable phenomena of our own world will always be favored over one that requires us to invent new forms of energy, new methods of communication, and the convenient arrival of an intelligent, or at least technologically active, interstellar object. This is not a failure of imagination. It is the very heart of the scientific method. It is a disciplined process of elimination, a meticulous sifting of the probable from the improbable. The burden of proof lies squarely on those who propose the extraordinary connection to 3I ATLAS. It is not up to the skeptics to disprove it. It is up to the proponents to provide evidence so compelling, so unambiguous, that it can withstand the onslaught of every one of these more mundane terrestrial explanations. They must demonstrate that the hum cannot be explained by pipelines or waves or wind or wires. They must show a clear causal link that defies the physics of the vacuum and the atmosphere. And so we are left standing in the quiet of the courtroom, the weight of the evidence for skepticism hanging heavy in the air. The case for a prosaic origin for the hum seems overwhelming. The vast distances, the silent void, the atmospheric shield, and the sheer number of Earth-based suspects all point to a single verdict. The connection to 3I, Atlas, is a captivating fantasy, a modern myth born from coincidence and our deep-seated yearning for contact. The rational mind is compelled to agree to close the case file and move on. The mystery, it seems, was never in the sky but right here on the ground, or perhaps even within ourselves. And yet, for some, that conclusion feels incomplete. It doesn't quite account for the strangeness of the timing, the eerie global synchronization that seemed to follow the comet's trajectory. It struggles to explain why so many disparate reports from different locations and different terrestrial environments shared such a uniquely similar character. While the wall of skepticism is high and well built, a few researchers wondered if there wasn't perhaps a small overlooked crack in its foundation, a single anomalous thread that, if pulled, might just unravel the entire case for the mundane. Their search would take them away from broad speculation and into a forensic-level analysis of a new and entirely unexpected set of data. And so the trail went cold. The correlation, that tantalizing ghost of a connection between the arrival of our interstellar visitor and the strange global thrumming, remained just that, a ghost. Direct evidence was non-existent. Every attempt to trace a clear, unambiguous line from the fading light of 3I, Atlas, to the infrasonic pulse in our planet's atmosphere had dissolved into statistical noise and scientific skepticism. For many, the case was closed, the verdict delivered coincidence. A fascinating, mind-bending coincidence, but nothing more. The hum would return to its file, a curiosity for cryptoacousticians and late-night radio hosts, while the comet would become another footnote in the celestial catalogue. It was a deeply unsatisfying conclusion, a cosmic mystery that had simply evaporated under the harsh glare of scrutiny. The universe, it seemed, was not ready to give up its secrets so easily, but in science an ending is often a disguise for a new beginning. A dead end is not a wall, but a sharp, unexpected turn, forcing us down a path we never intended to travel. The failure to find a simple answer, a straightforward cause and effect, did not kill the inquiry. Instead, it transformed it. The question, so simple at first, did that object cause the hum, was revealed to be painfully naive. It was like asking if a single raindrop caused a flood. The real mystery was far more profound, far more complex. The community of researchers drawn to this puzzle realized they were not just chasing a sound. They were standing at the precipice of a new and unnerving frontier in planetary science. If they couldn't observe the event directly, if the past was forever lost to them, then they would do the next best thing. They would build it. They would forge a new reality from silicon and code, creating a digital ghost of our solar system, a computational oracle where they could replay the encounter not just once, but 1,000,000 times under 1,000,000 different conditions. We were about to witness the birth of a new kind of cosmic exploration, one conducted not with telescopes and probes, but with the boundless power of supercomputers. In sprawling climate-controlled rooms, bathed in the cool blue light of server racks, teams of astrophysicists and plasma physicists began constructing a digital twin of 3I, Atlas's journey. They fed these computational engines everything we knew: the object's estimated mass, its bewildering velocity, its trajectory that sliced through the ecliptic plane like a shard of glass. They meticulously modeled the sun's magnetic field, the density of its solar wind, and the delicate, invisible shield of Earth's own magnetosphere. They were building a universe in a box, a virtual stage upon which they could resurrect their interstellar ghost and force it to reveal its secrets. The goal was no longer to prove that 3I Atlas times did times cause the hum, But to answer a far more fundamental and electrifying question, could it have? Was there any known physics, any plausible mechanism by which an object like this, a silent traveler from the void, could make its presence known to us not through light but through sound? The first simulations began to run, consuming megawatts of power, crunching quadrillions of calculations per second. And as the data began to pour out, translating into vast, complex visualizations, the first hints of a possibility began to emerge. It was a mechanism born of pure violence, a process that unfolds when an object travels not through a vacuum, but through the tenuous, electrically charged ocean of the solar wind. You see, interstellar space is not truly empty. It's filled with a thin soup of particles, a plasma that our sun constantly replenishes with its own stellar breath. To something moving at typical solar system speeds, this medium is negligible, but 3I Atlas was anything but typical. It was a cosmic speedboat moving at a velocity so extreme that the solar wind wasn't a gentle breeze, it was a wall. The simulations showed the object carving a channel through this plasma, creating a phenomenon known as a bow shock, the invisible equivalent of a sonic boom. Imagine a phantom vessel, 1 billion tons of ice and rock tearing through the fabric of the solar system at over 100,000 miles per hour. Ahead of it, the solar plasma, caught utterly by surprise, compresses, heats up, and becomes turbulent, a chaotic wave of energy preceding the object itself. But it was what happened times behind times, the object that truly captivated the researchers. In its wake, 3I Atlas left a vast, trailing cone of disturbance, a swirling vortex of plasma instabilities that stretched for millions of miles. This was not a silent, clean passage. It was a messy, violent, and electrically noisy event. Within this cosmic wake, the simulations showed magnetic field lines carried outward from the sun being stretched, twisted, and snapped like rubber bands. This process, known as magnetic reconnection, unleashes furious bursts of energy, accelerating particles to near-light speed and generating powerful waves, not sound waves, but plasma waves, ripples in the electromagnetic fabric of space itself. The digital visualizations were breathtaking. We could see this turbulent wake, a ghostly shimmering tail interacting with the planets. As 3I Atlas passed by, its wake would have washed over Earth's own magnetic bubble, the magnetosphere. It wouldn't be a physical impact, but an electromagnetic one. This plasma tempest, this storm of magnetic chaos, would have slammed into our planet's first line of defense. The models suggested this interaction could be profoundly complex. The plasma waves traveling down the wake could have coupled with our magnetosphere, causing it to vibrate, to resonate, like a vast invisible drum skin being struck by a spectral hand. These vibrations, these ultra-low frequency oscillations of our entire planetary magnetic field, are not sound, but they are a form of energy. And the question that hung in the air, the central thesis of this new inquiry, was whether that energy could find a way to translate itself, to cascade down from the vacuum of space into the dense medium of our atmosphere. Could the magnetosphere, in its shuddering response to this cosmic assault, act as a kind of colossal transducer? Could its vibrations exert a subtle but measurable pressure on the uppermost, most fragile layers of the ionosphere? And could that pressure in turn create a cascading wave, a pressure front that propagates downwards through the thinner layers of the mesosphere and stratosphere, growing in amplitude as the air gets thicker, until it finally manifests in the troposphere as infrasound, a sound so low it's felt more than heard, a planetary hum generated by a celestial visitor that passed millions of miles away. The simulations could not provide a definitive yes. The physics of this coupling between the magnetosphere and the atmosphere is one of the most complex and poorly understood areas of planetary science. But for the first time, they showed it was plausible. They provided a physical chain of events, a sequence of credible steps that connected the silent passage of an interstellar rock to a sound that could theoretically be heard by the most sensitive instruments on Earth. It was no longer science fiction. It was a legitimate, albeit radical, hypothesis grounded in the hard data of computational physics. But the plasma wake was not the only ghost the simulations revealed. Another team of theorists, intrigued by the object's peculiar trajectory, decided to model a different kind of influence, one far more subtle, ancient, and fundamental. They wanted to explore the whisper of gravity itself. We tend to think of gravity as a simple pull, a constant force that anchors us to the ground and holds the planets in their orbits. But on a cosmic scale, gravity is a dynamic fluid force. Massive objects moving through space create ripples, disturbances in the very fabric of space-time. And while 3I Atlas was not massive enough to generate the kind of gravitational waves we can now detect from colliding black holes, its unique combination of high speed and an unprecedented trajectory presented a different possibility. It might not have created a gravitational wave, but it could have acted as a gravitational metronome, a transient rhythmic influence on the delicate dance of our own local system. Their models focused on the concept of gravitational resonance. As 3I Atlas sliced through the inner solar system, its gravitational field, though small compared to the Sun or Jupiter, was not insignificant. It was a foreign influence, a new beat in the ancient rhythm of our celestial neighborhood. The simulations explored whether this passing field could have induced a subtle resonant forcing on the Earth-Moon system, or even on the geologically active plates of our own planet. Think of pushing a child on a swing. A single powerful shove will move them, but it's the gentle rhythmic pushes timed perfectly with the swing's natural frequency that send them soaring. Could 3I Atlas during its brief but rapid transit have provided just such a rhythmic push? Could its gravitational pull, fluctuating as it approached and receded, have locked into a natural resonant frequency of our planet's crust or its deep liquid core? The idea was almost heretical, pushing the boundaries of geophysics. Yet the numbers churning inside the supercomputers began to paint a fascinating picture. They modeled the minute tidal stresses exerted by the object on Earth's lithosphere. They found that for certain models of the object's mass and density, its passage could have excited what are known as the normal modes of the Earth, the planet's own natural vibrational frequencies. Our world is not a solid inert rock. It is a living, breathing body that constantly rings like a bell at a set of ultra-low frequencies far below the threshold of our hearing. These vibrations are usually triggered by large earthquakes, but the simulations showed that a powerful external gravitational disturbance passing by at just the right speed and distance could theoretically pump energy into these modes, increasing their amplitude. It would be the equivalent of a cosmic hand gently strumming the entire planet. This gravitational whisper would not create a sound in the air directly. Instead, it would manifest as a tiny, almost immeasurable increase in the background seismic vibration of the planet itself, a global, coherent trembling of the very bedrock beneath our feet. And from there, the connection to the hum became tantalizingly direct. Any large vibrating surface will move the air above it, producing sound waves. A planet ringing like a bell, even imperceptibly, would create a vast planet-sized infrasound wave in the atmosphere that perfectly matches its own vibrational frequency. The researchers had found a second, entirely independent physical mechanism. One model proposed a tempest in the plasma, the other a tremor in the rock. Both were born from the same source, the fleeting passage of a messenger from another star, and both converged on the same outcome, a persistent, low-frequency hum, global in scale and mysterious in origin. This was the climax, not a discovery but a revelation. The simulations had not handed us an answer on a silver platter. They had not produced a sound file that, when played back, matched the Taos hum or the Windsor hum. They had done something far more important. They had shattered our assumptions about the silence of space. They had demonstrated with rigorous model-based evidence that the solar system is an interconnected web of forces where an event in one region can have subtle, unexpected consequences millions of miles away. The question was no longer about a single comet and a single strange sound. It had exploded into a paradigm shift. We had been forced to reframe our entire understanding of cosmic influence. Terrestrial explanations for the various local hums around the world, industrial noise, seismic activity, tinnitus, remained the most logical and primary cause in most cases. That had not changed. What had changed was the possibility that not all times of these phenomena had to be local. We had accidentally stumbled upon a new frontier, the potential for a new science, cosmic acoustics. The study of how events beyond our world, the passage of interstellar objects, the shockwaves from solar flares, the gravitational jostling of other planets, can be translated into acoustic or seismic signatures here on Earth. It was a radical idea suggesting that our planet is not an isolated lifeboat in a silent void, but a sensitive receiver, a planetary microphone tuned to the faint, deep harmonies of the cosmos. We had been searching for a signal, a message, but perhaps what we were hearing was simply the background noise of the universe's machinery, a hum generated by the simple, elegant, and powerful mechanics of physics playing out on a grand scale. The journey to understand 3i, Atlas, had inadvertently given us a new sense, a new way to listen to the heavens. And with this new sense came a new kind of hunt. The focus shifted away from proving the past and towards preparing for the future. If objects like 3i, Atlas, can leave these subtle fingerprints on our world, how do we equip ourselves to detect the next one? The simulations had not just provided theories, they had provided a roadmap. They predicted specific signatures we should be looking for, characteristic oscillations in the magnetosphere, specific modes of seismic vibration, unique polarizations in atmospheric infrasound. Suddenly, data from instruments that were never designed for astronomy became critically important. Global networks of magnetometers, seismometers, and microbarometers built to monitor solar storms and earthquakes were now being re-examined as a de facto interstellar observatory. Teams began developing sophisticated new AI algorithms designed not to search for a single repeating signal, but to scan petabytes of planetary monitoring data for faint transient correlations to find the fleeting moment where the pulse of the Earth changes in sync with an event in the sky. The search for 3i, Atlas's connection to the hum, had failed, but in its failure, it had launched a far grander and more ambitious quest. It had taught us that to truly understand our place in the universe, we can't just look up. We must also listen down. We must learn to read the subtle language written in the tremors of our own world, to hear the echoes of distant events in the vibrations of the very ground beneath our feet. The visitor was gone, a fading memory on a photographic plate. But it had left behind a profound and lasting gift, a new direction, a new mystery, and the tantalizing promise that the next time a messenger from the interstellar darkness graces our solar system, we will be ready, we will be listening. And so, after a journey that has taken us from the quiet desperation of a bedroom in Bristol to the cold, silent vacuum of interstellar space, we find ourselves standing at the edge of a great unanswered question. The elegant, unifying thread we sought, the direct causal link between the maddening terrestrial hum and the fleeting passage of 3i, Atlas, remains just beyond our grasp. The data sifted and cross-referenced by a global consortium of the world's finest minds offers no definitive verdict. There is no celestial smoking gun, no unambiguous signal echoing from that distant, disintegrating messenger to the sensitive diaphragms of our planet's most advanced detectors. For some, this might feel like a failure, a grand and expensive expedition that returned with empty hands. But that would be a profound misreading of the map, a failure to appreciate the unexpected territories we have charted along the way. The true discovery was never going to be a simple yes or no. The real prize was in learning how to ask such an audacious question in the first place. What began as a speculative leap, a wild hypothesis born of frustration and curiosity, has inadvertently become one of the most fruitful scientific endeavors of our time, leaving behind a legacy far richer and more complex than any single, simple answer could ever have been. We must remember where this story began with people. Individuals, isolated by an invisible torment, their suffering dismissed as tinnitus, as psychological aberration, as the product of overactive imaginations. For decades, the hum was a ghost, a phantom haunting the fringes of acoustics and geophysics. The scientific community, focused on grander, more easily quantifiable phenomena, had little time for a low-frequency nuisance that defied easy explanation. But the bold, almost reckless proposal to connect this terrestrial mystery with an interstellar object fundamentally changed the conversation. It elevated the hum from a localized curiosity to a global scientific imperative. Suddenly, the most sensitive instruments on Earth were pivoted, their purpose redefined, their digital ears strained to hear this planetary whisper. The very act of searching for a cosmic source forced us to build a global listening network of unprecedented scale and sensitivity, uniting disparate research stations from the Antarctic Plateau to the quietest deserts of the Atacama. This planetary-scale microphone, this global infrasound observatory, is perhaps the investigation's most significant tangible legacy. It was built to hunt for an alien echo, but what it has found is the previously hidden symphony of our own world. Through this network, we have begun to compile an entirely new atlas of Earth's secret sounds. We are now able to track the low-frequency rumble of remote volcanic eruptions in real time, watching their atmospheric pressure waves propagate across entire oceans like ripples in a pond. We can hear the birth of distant storms, their barometric hearts beating a slow, powerful rhythm that was previously lost in the noise. Scientists are using this new infrasound data to map the complex, turbulent dance between the ocean's surface and the upper atmosphere, identifying mysterious energy transfer mechanisms that shape our climate in ways we are only just beginning to comprehend. We have detected the subtle groans of tectonic plates shifting deep beneath the seabed, providing a potential new avenue for earthquake and tsunami early warning systems. These are not minor discoveries. They are fundamental advances in our understanding of Earth as a dynamic, interconnected system. We went looking for a voice from the void and discovered with stunning clarity the very voice of our own living planet. We have learned to distinguish the growl of the lithosphere from the sigh of the atmosphere, charting the planet's ceaseless, vibrant monologue. This radical shift in perspective has also permanently altered the field of astronomy itself. The passage of 3I, Atlas, and the tantalizing possibility that it was more than just a silent rock has shattered old paradigms. Before this, our search for extraterrestrial intelligence, and indeed our study of interstellar objects, was almost entirely visual. We looked for light, for radio waves, for the familiar signatures of communication as we understand it. The notion of searching for a low-frequency vibrational or acoustic-adjacent signal from a celestial body was confined to the realm of science fiction. No longer. Astronomers and engineers are now actively designing new observation protocols for future interstellar visitors. When the next Oumuamua, or Atlas, streaks through our cosmic neighborhood, we won't just be looking at it, we will be listening to it. Telescopes will still track its trajectory and spectral composition, but they will be working in concert with a global network of infrasound detectors with repurposed gravitational wave observatories, with every tool at our disposal that can perceive the universe through a non-visual medium. We are learning to be sensitive to cosmic whispers, not just cosmic shouts. The investigation has compelled us to reconsider what a signal even is. Could an object like 3I, Atlas, a loosely aggregated collection of ice and dust, generate a coherent low-frequency hum as it sheds material and interacts with the solar wind's magnetic field? The physics remains speculative, pushing the boundaries of plasma dynamics and magnetohydrodynamics. Yet, the very act of modeling these scenarios has opened up new avenues of theoretical research. It forced us to see such objects not as inert debris, but as potentially active dynamic systems capable of interacting with their environment in ways we had never imagined. It's a profound conceptual leap. We have begun to view the solar system not as a silent clockwork mechanism, but as a vast resonant chamber where gravitational tides, magnetic fields, and streams of charged particles could potentially interact to produce a subtle underlying music. This quest has imbued the cosmos with a new and strange potential for sound, transforming our perception of the silent void into a place of hidden, vibrant energy. The universe, it seems, may not be as quiet as we once believed. We simply lacked the proper instruments, the proper framework to hear its deepest notes. And what of the hum itself, the mystery that started it all? Has it been forgotten in this grand cosmic diversion? Far from it. By eliminating the extraordinary possibility of a single global extraterrestrial source, we have been forced to look more closely and more seriously at the extraordinary complexity of the terrestrial sources. The investigation has not solved the hum, but it has legitimized it. It has transformed it from a phantom into a formidable scientific challenge. The data from our new global network has confirmed that there is no single hum. Instead, we see a complex and shifting tapestry of low-frequency noise, a layered phenomenon with dozens, perhaps hundreds of contributing sources. In one region, the dominant source may indeed be the ceaseless rhythmic pounding of ocean waves on a specific piece of continental shelf, a process known as microsisms, where the energy of the ocean is converted into a vibration that travels for thousands of miles through the Earth's crust. It is the planet's own heartbeat, a sound we feel more than we hear. In another area near industrialized zones, the hum is clearly a harmonic convergence of machinery, the drone of massive ventilation systems, the thrum of high-pressure gas lines, the resonant frequency of power station turbines, all blending into a single maddening chord that can travel for miles. Through the ground, its pitch and intensity shifting with the rhythm of the workweek. Our investigation has shown how these industrial sounds can be amplified by local topography, trapped in valleys or funneled for miles along specific geological formations, explaining why one town might be plagued by the sound while a neighbouring one remains blissfully unaware. We have even discovered purely atmospheric sources, strange standing waves created by the interaction of high-altitude jet streams with mountain ranges generating columns of vibrating air that can create a persistent low-frequency, drone audible only under specific weather conditions. So the hum is not one thing. It is everything. It is the complex, sometimes dissonant auditory signature of a planet inhabited by both powerful natural forces and a burgeoning technological civilization. We have come to understand that we live inside a vast planetary instrument, and we are only now beginning to identify all the players in its orchestra. This journey has also revealed something profound about the nature of science and the human spirit. It began with an act of profound empathy, scientists taking seriously the lived experience of ordinary people. The connection to 3I, Atlas, while ultimately unproven, acted as a catalyst, providing the necessary narrative momentum to secure funding to unite international teams and to justify a truly ambitious research program. It was a Trojan horse, a spectacular cosmic story that smuggled a vital piece of terrestrial research into the gates of mainstream science. It reminds us that sometimes the most significant progress comes not from methodical incremental steps, but from a wild imaginative leap that, even in failing to reach its intended destination, discovers entirely new continents of knowledge along the way. It is a testament to the power of asking what if. The question, what if the hum is from space, has yielded a far more powerful and useful result than we could have ever anticipated, a comprehensive global initiative to finally understand the true soundscape of our world. Moreover, this entire endeavour has forced a necessary and humbling realignment of our cosmic perspective. For centuries, we have looked to the stars with a sense of visual grandeur, charting galaxies and measuring light. But this investigation has been about a different kind of connection, a more intimate and subtle one. It's about the possibility that we are not just observers of the universe, but resonators within it. The idea that a passing fragment of another solar system could cause our own world to vibrate to hum in sympathy is a poetic and powerful one. It speaks to a deep-seated human desire for connection, for a sign that our small, isolated world is part of a larger, interactive whole. While 3I, Atlas, may not have been that sign, the search for it has awakened us to other real cosmic resonances. We live on a planet that is constantly ringing from the impact of micrometeorites, a world whose magnetic field sings as it is struck by the solar wind, a rocky body that is ceaselessly stretched and squeezed by the gravitational pull of our moon and Sunday. We are not separate from the cosmos. We are embedded within its physical and energetic web. This new awareness changes how we perceive our place in the universe. It suggests that if we ever do find evidence of life beyond Earth, it may not come in the form of a Hollywood-style radio broadcast. It might be far stranger, more subtle. It could be a rhythmic fluctuation in a distant star's magnetic field, a persistent vibrational anomaly from a rogue planet, or an impossibly complex low-frequency pattern emanating from the atmospheric friction of an alien megastructure. By learning to listen for our own planet's hum, we have inadvertently begun our first real lesson in this new form of cosmic listening. We are training ourselves to find the signal in the noise, to look for patterns not just in light and energy, but in the very fabric of space-time and the subtle vibrations that pass through it. The search for the hum's source was a dress rehearsal for a much grander search, one that will likely define the future of astronomy for centuries to come. So, where does this leave us? We stand here at the end of our story with two truths held in a delicate balance. The first is that the universe is under no obligation to give us the simple, dramatic answers we crave. The link between the hum and 3i, Atlas, remains a beautiful, unproven hypothesis, a ghost of a possibility that will likely linger in the scientific imagination for generations. It is a modern myth, a story we tell ourselves about our potential connection to the vast and mysterious cosmos. The second, more concrete truth is that the pursuit of this myth, the disciplined, passionate, and collaborative search for evidence, has rewarded us beyond measure. It has armed us with new tools, new knowledge, and an entirely new sensory modality with which to perceive both our own planet and the universe beyond. We have not failed, we have succeeded in ways we never intended. We have expanded the very definition of what it means to observe. We are left not with a neat conclusion, but with a profound and enduring sense of wonder. We are left with the image of our planet, a blue marble hanging in the blackness, no longer silent but alive, with a complex chorus of sounds. We hear the deep, slow rhythm of the oceans, the powerful rush of the wind, the seismic groan of the continents, and layered over it all the persistent technological drone of our own civilization. And looking out beyond our atmosphere, we no longer perceive a silent void, but a place of immense potential, a resonant expanse filled with energies and vibrations that we are only just beginning to learn how to detect. The mystery of the hum has not been solved so much as it has been transformed. It has become a gateway to a dozen other deeper mysteries. The connection to 3i, Atlas, may be lost to the darkness, but it has illuminated our world and our universe in a brilliant, unexpected and lasting light. And now, when you stand outside on a quiet night, you might find yourself listening not just with your ears, but with your entire being, straining to hear the subtle, complex music of the world and wondering what other cosmic notes might be, waiting in the endless quiet, patiently waiting for us to finally learn how to listen. The search is far from over. In truth, it has just begun.